Okay, so this afternoon session progresses with my own student, Sarah Petersen, who's going to speak on a spectrum level splitting of the KUR cooperations algebra.
All right, thank you very much for the introduction, and thank you to all the organizers, both of the program. It's been really wonderful to get to spend time here off and on throughout the semester and to talk to collaborators, and also this conference. I've been really enjoying hearing all of the ideas presented so far. So, as Mark said, I'm going to be speaking about a spectrum level splitting of the KUR cooperations algebra. All of this is joint work with Gu-Chuan Lee and Elizabeth Tatum, both of whom are in the audience today. And I'd like to begin with a little bit of background and context for this problem. So this originated in ideas that were being studied back in the 70s. Brown and Gittler constructed what are now called Brown-Gittler spectra, which are spectra realizing certain subcomodules of the dual Steenrod algebra. And while these were constructed with the intentions of being very useful in studying immersions of manifolds, Mahold realized that these spectra are indeed very helpful in homotopy computations. So for instance, he observed that these can be used to decompose HC smash HC in terms of a finite sum of HC modules, and also constructed an integral analog of Brown-Gittler spectra. So these integral versions, they realize subcomodules of the homology of HC. And these constructions were useful because they also allowed Mahold and Kane to construct splittings of both KU and KO in terms of the finite modules. So why would one care about having these sorts of splittings? Well, because if you're interested in homotopy as an invariant, one of the tools we have that's really useful for computing homotopy is the atom spectral sequence. And we have lots of different types of atom spectral sequences so for instance, one can do KO or KU-based atom spectral sequences. And these can give different information about the homotopy groups of the state. And if we want to compute these atom spectral sequences, well, we'd like to maybe start at the E2 page and just compute an X group. But in the case of KO or KU, KO star KO or KU star KU, neither of these are flat over the coefficients. So we need to start back at the E1 page and compute that first. And Mahold and Kane's splittings really made a computation of these E1 pages tractable. And with a little bit more work, you can also get to the E2 page fairly easily. And these have a wealth of information. So specifically, they really highlight V1 periodicity in the stable stems, and also have vanishing lines, which result in collapse of the spectral sequence in a large range. In particular, the KO-based atom spectral sequence is what Mahold used to prove the telescope conjecture at the prime 2 and height 1. And Gonzalez used the KU-based atom spectral sequence to classify stunted length spaces. So very much in fitting with the themes of this program, Liz and Gu-Chuan and I were wondering if there are any equivariant analogs of these sorts of splittings, and also like what sorts of computations could you do if you had those equivariant analogs. So the first question you might ask when thinking about any equivariant analog is, what group of equivariants should we choose? And of course, like, the answer is usually, well, start with the simplest thing. But here, the simplest thing, and the simplest thing does usually turn out to be pretty challenging already. But the simplest thing, the cyclic group of order 2, well, the dual Steenrod algebra is computed, so that's certainly good. And moreover, it also looks fairly similar to the non-equivariant dual Steenrod algebra. So we'll set G equal to C2. And a little while back, Hahn and Wilson realized that there are indeed analogs of Brown-Gittler spectra realizing subcomodules of the C2 equivariant dual Steenrod algebra. So this would be useful for splittings of HZ smash HZ, where here Z is now Z underline, with being the C2 constant Mackey functor Z, and HZ being the Eilenberg-MacLean spectrum for that constant Mackey functor. And with this project in mind of constructing KUR splittings, Liz Gutschwan and I thought about whether we could construct integral analogs of those C2 equivariant Brown-Butler spectra, and indeed we did. So in this C2 equivariant setting, we already have all the pieces we need to at least hope that maybe we could construct such a splitting. And at odd primes, one could certainly ask a similar question because the CP equivariant dual Steenrod algebra has been computed. But as that's not even free over the coefficients, the computational techniques you need would probably be much more involved. And also, I think at this point, it would be really not clear whether you should expect a splitting or not, even for those additional groups. Okay, so let's get into constructing a splitting for KUR smash KUR. And to do that, I want to tell you a little bit more about C2 equivariant integral Brown-Butler spectra. So we're going to define a weight filtration on the homology of HC. So we have generators Ci and tau I. These live in equivariantly graded degrees. But we're going to set the weight of Ci to be 2 to the I, the weight of tau I also to be 2 to the I, and define our weight filtration by the weight of the multiplications, the sum of the weights. And then B sub 0 of K is going to denote the Brown-Butler spectrum, realizing the subcomodule of the homology having weight at most K. So the first step in constructing such a spectrum level splitting is, well, if you want to have something exist on the level of spectra, you should probably be able to observe it in homology first. It's usually much easier to compute. So we started there, and there we observed there is an E of 1 comodule isomorphism between the homology of shifted suspensions of the C2 equivariant Brown-Butler spectra and the homology of KUR. So KUR here, this is the equivariant cover of the spectrum representing Atiyah's real K theory. And this splitting in homology goes very similarly to the non-equivariant splitting. One can write down a very explicit isomorphism. It's not very limiting, so I won't show you that here. But it can be found both in our preprint and in work of Dominic Culver in the non-equivariant setting. So, given this E of 1 comodule isomorphism, our goal is going to be to construct a family of KUR module maps such that we get our desired equivalents. And to do that, we're going to use a KUR relative atom spectral sequence to lift the E of 1 comodule equivalents to the level of spectra. So just a reminder about relative homology. In general, if E is an R algebra and M is an R module in spectra, then the E homology in the category of R modules is the homotopy of E smashed over R with M. And in particular, notice that if we were to take the homology in this relative category of R smash M, this is isomorphic to just the ordinary non-relative E homology of M. So we can use this isomorphism to rewrite our E of 1 comodule isomorphism in terms of relative homology. And that's what we do here. So writing this isomorphism in terms of KUR relative homology means that we're now ready to compute the KUR relative atom spectral sequence, which has this as on the left as its E2 page and converges to what we want. So in particular, the KUR relative atom spectral sequence, this is finite in each of the degrees, so this does converge, so that's certainly good. And in particular, the maps theta k that were appearing in our E of 1 comodule isomorphism, well, these live in E00. Here, the grading on this is tri-graded. We have the stem, filtration, and then also a motivic weight. So constructing the desired maps on the level of spectra is the same as showing that these maps survive the spectral sequence. So our new goal is going to be to show that they actually do indeed survive. And our first step is going to be to decompose the KUR relative spectral sequence into a sum of simpler spectral sequences. So we begin this process by observing that there are KUR module splittings. And what these KUR module splittings do is they split up the KUR smash B0, the integral Brown-Gittler spectra, into a summation where the first sum has no suspensions of the Eilenberg-MacLean spectrum, and the second sum, the BK, or just B, contains all the summations of the Eilenberg-MacLean spectrum H. So we're taking what we have and separating out the Eilenberg-MacLean stuff and the non-Eilenberg-MacLean stuff. And what this proposition allows us to do is then take the KUR relative atom spectral sequence that we're interested in and decompose it into a sum of 4 simpler spectral sequences. So one with the parts C sub k and C, so we get one of these for each k. One with the parts C sub k and B. One for the B sub k's and c's, and one with the B sub k's and b's. Now, the last 3 of these spectral sequences, the B sub k and b, since these are Eilenberg-MacLean, they are free E of 1 modules. So all of the last 3, they're concentrated on the f equals 0 line. So we won't study them in detail. And what we really have that's interesting to compute is this portion of the atom spectral sequence, the portion involving the C's, sub K's, and the C's. So we're going to begin by computing this E2 page, which means we want to compute these X groups. And to do that, I first need to tell you what the homology of these spectra are. So I'm not going to go fully into how the C sub k and C are constructed. This has to do with the homology of the C2 equivariant Brown-Gittler spectra, for instance, so that's one of the ingredients that goes into this. But essentially, the KUR relative homology of both of these, all these spectra, is given in terms of equivariant lightning flash modules. So these are analogs of the lightning flash modules that appear in non-equivariant homotopy theory. So here is a picture example. So we have some generators, x1. This picture in particular is graded so that the topological degree is on the horizontal axis, and the vertical axis is the number of sign representations. So x1 is living in degree rho plus 1, x2 in degree 2 rho plus 1, x3, 3 rho plus 1, and so on. And the curved arrows, these represent an action by q1, and the straight arrows an action by q naught. So in mathematical symbols, here is the definition of the length k lightning flash module. And in particular, we define the 0th lightning flash module to just be a copy of the coefficients m2. So given that the homology of the spectra we are interested in decomposes into these lightning flash modules. To compute this E2 page, it's going to be sufficient to be able to compute x over E of 1 of all these various length lightning flash modules. So that's what we'll do next. So our strategy for that is going to begin by setting the first factor, k equal to 0, so that we're computing x over E of 1 of m2 L of m. And we're going to induct on m using a short exact sequence in the lightning flash modules. So if we go back to the previous slide, we can envision how if we truncated this at x3 and took the row suspension, well, this would move this x3 up to where x4 is, and it would lay on top of everything from this point connected to here. And so we'd only have these 2 points left over with this one arc, and that's exactly what we see as our third term in the short exact sequence. And after doing that, then we'll fix m and induct on k to compute the x groups in general. Any questions so far? Okay. So to run our induction, of course, we need to start with the base case. And with, since when k is 0 and m equals 0, this is just x over E of 1, m2. And this was computed by Yu, Hill, Isaacson, and Ravenel. So to tell you what that x group is, it's helpful to have a little bit more in-depth discussion of the coefficients m2. So this picture may be familiar to many of you. Here we're going to be using the motivic notation for the elements in homology. So we have a positive cone part, which is polynomial on elements rho in degree -1, and tau in degree 0, -1. So these are the homological gradings. And we also have a negative cone portion on a generator which we're calling gamma over tau, so almost imagining as if gamma lived at 1, 0, but it's actually not there. And the negative cone generator is infinitely divisible by both rho and tau. So what's useful about this description of the coefficients is that, well, they are a square zero extension of the positive cone, which is isomorphic to the real motivic coefficients, direct sum of the negative cone, and this is as an F2 of tau module. So Yu, Hill, Isaacson, and Ravenel use this to observe that this descends to a splitting also on x. In general, there's also a Tor term, but it vanishes in this particular case. And we get something that's a summation of x over the positive cone part with a negative cone summand as well. So to simplify notation a little bit for this talk, instead of having all the decorated R's and M's, we'll simply use the notation with the plus sign to denote the positive cone summand and the minus sign to denote the negative cone summand. So I want to tell you what this X group is, and the first portion of that is the positive cone portion. And this was computed by Mike Hill a few years back. And it's polynomial on a number of variables with a few relations. Now, each of these have a stem, a filtration, and also a motivic weight. So it's useful to visualize these things using charts. So we'll walk through a visualization of that. So if we just start with tau to the fourth, the way the rest of the pictures are going to go in this talk is we'll have the stem along the horizontal axis, the filtration F is on the vertical axis, and then the weight does not appear at all. So tau to the fourth, this is in stem 0, filtration 0, so it's appearing at 0, 0 in our chart, and it has weight -4. So you can imagine it as like a tower of tau to the 4th, tau to the 8th coming out towards you. And then the next element is rho. Rho is in STEM -1, filtration 0. And since the weight is left to the imagination, I won't bother describing it for the rest of them. So what multiplication by rho does is it's going to take us 1 unit to the left. So rho lives here, multiplication by rho again would be at -2, 0, and so on. So because there's no relation with rho and tau to the 4th, that we have just an arrow pointing to the left there. And then adding in V0. V0 is in filtration 1, so this multiplication by V0 gives us an F2 tau to the 4th tower here, and we have our first relation appears that rho V0 is 0, so because of that, we get no further towers of rho multiplication going off to the left. And then our next element is V1. V1 is in STEM 2, filtration 1, so appearing here in our chart, and we get all of the multiples of that. And we also have our next relation, that rho cubed V1 is 0. So if we look at V1, we multiply by rho, get to rho V1, multiply to rho squared V1, but rho cubed V1 is 0. So that's how we get a chart of this shape. And then finally, we also have tau squared, V0. We'll be denoting this just in another chart as like the part B of that same summand. There is a multiplicative relation there, but this won't be too important for like the context of this talk. It just says that if we were to square something in this tower, it does match up with the blue towers on the left. Okay, any questions? All right, so this is our positive cone summand. Guillou, Hill, and Isaacson computed the negative cone summand as well, and this is as a module over the positive cone summand. So going through pictorially, now instead of tau to the 4th towers coming out towards you, in the negative cone summands, we have like 1 over tau to the 4ths going back away in the opposite direction. And we also have divisibility by rho. So since multiplication by rho takes us 1 to the left, dividing by rho is going to take us 1 to the right. So we have a division by rho tower here. We have V0 towers here. We have some multiplications by rho. And then we also have some additional V0 towers. So as a whole, putting together both the positive cone summands, which will appear in the top half, and the negative cone summand, which will appear in the bottom half, we get a full chart that looks like this. Now to simplify things, you can always just like focus on like positive cone summand part A, and this also reduces or recovers the classical KUs, one possible construction of the classical non-equivariant KU splitting, in that you can collapse all the multiplications by rho, just forget about those, and also set tau just equal to 1, and then you would recover charts that would match the non-equivariant story. Okay, so we have the base case. This is already computed for us, and what we're really interested in is the rest of these X groups. So we're going to use our short exact sequence. This indeed induces a long exact sequence relating X groups that we're interested in to things we hopefully know. And so one term we have remaining also to compute is this x over e of 1, m2, e of 1, mod e of 0. And by change of rings, this is isomorphic to x over e of 0, m2, m2. So we're going to need to understand that as an x over e of 1 module as well. And these pictures are not so different. They're a bit simpler. So the positive cone summands, the dots represent tau to the 4th towers. We have V naught multiplications and row multiplications, both on 1 and on tau squared. And the native cone picture really mirrors that as well. We have a V naught tower in each of those subbands and a row divisible tower as well. And putting the pictures all together, x over e of 0 looks like this. And as a reminder, x over e of 1 looks like this. So we're going to begin putting both of these together using our long exact sequence. And in particular, our long exact sequence tells us that we should have what the x groups we're interested in. These sit in a long exact sequence in between x over e of 0's m2, m2, and row fold suspensions of x over m2, and then the previous length lightning flash module. So what we should do to figure out these x groups is take the lightning flash module from the previous one, so x over e of 1 gets shifted by row, and shifting by row is going to increase the stem by 2, so this gets shifted 2 over to the right, so you'll see in the blue and a green a copy of x over e of 1. And then we also have a copy of x over e of 0 appearing at with no shift. And for these, there's no possibility of differential because the differential will shift us back in stem by 1, and the x over e of 1 term is to the left of everything else. So we can continue this type of induction, shifting everything to the right by 2, and then inserting an x over e of 0, and get pictures like this. And so in general, our x over e of 1, m2, L of m groups have this format. So far, where we are in this problem is we've reduced our study of the KUR relative atom spectral sequence to a simpler spectral sequence. And we also observed that we want to compute the E2 term in terms of x of these lightning flash modules, and we've computed about half of them so far. So our next task is for k to be greater than 0 as well. And so we're going to fix m greater than 0, use the same short exact sequence to introduce a different long exact sequence. And in this long exact sequence, we have x e of 1 mod e of 0 in the first factor now. And so we'll need to use a Ronstadt way, change of rings isomorphism, that equates this x group to the minus rho minus 1 suspension of x over e of 0, which is something we already know. So using this to compute, inside the long exact sequence, we have a minus rho suspension of the previous x term. So this is going to shift an x group that we've already seen 2 over to the left. And then we'll insert the x over e of 0 at minus rho minus 1. And since the topological dimension of minus rho minus 1 is minus 3, that's why an x over e of 0 is appearing at minus 3. And then we need to compute, well, does a differential happen? And we can deduce that from either from like computing the Homs or reducing to the underlying non-equivariant computation and then deducing the rest through linearity. And so everywhere there's an arrow, those all happen. And so this x group, the answer looks like this. So not too much extra is happening compared to the x groups we saw before. We just additionally have some multiplication by row towers going off to the left. And we also have some divisible by row towers going to the right, but these are all in filtration 0. And this is indeed what happens in general. So for any k that's less than or equal to m, the x group is isomorphic to an x group with m2 and L of m minus k, direct sum some V0 and V1 torsion, which consists specifically of row towers starting in odd stem, infiltration 0, and infinitely divisible row towers infiltration 0 as well. So now we've computed everything where k is less than or equal to m, and what remains is to compute where k is greater than m. And these end up having a little bit more complicated form, which is the only reason why they separate it out. So still fixing m and inducting on k, our base case is going to be L of m plus 1, L of m. So for the example, we'll set m equal to 0 and just compute x L of 1, m2, using our long exact sequence. So now the x over e of 1 portion is shifted by minus rho. So you can see the x over e of 1 in blue and green shifted 2 to the left, so beginning at minus 2. And the x over e of 0 is inserted still at minus rho minus 1, so at negative 3 in these pictures. And this allows for differentials going from the blue or the green to hit the orange columns on the left. And these do indeed happen, which again one can deduce from the underlying and then using multiplicativity. So once one runs those differentials, you're left with a picture like this. We still have a portion that looks like x over e of 1, but a little bit messier remnants. And we could keep running this induction. So to do this again, we need to take this answer, shift it 2 to the left, and also insert a new x over e of 0 at minus rho minus 1. And if we do that, we get a picture like this. We have similar differentials. Running those differentials leads us to a picture that looks like this. And so we want to describe where all the elements are in these X groups so that we can then analyze the E2 page in our KUR relative atom spectral sequence and hopefully be able to deduce whether our elements theta k do survive. So to do so, we organize the elements in like a few different formations, mostly because it's a convenient way to keep track of them. So here are some that are in what we call the triangle formation. So the triangle formation here is like most obvious in the positive cone. It becomes more obvious in the negative cone as the first lightning flash module gets longer. There are also some row towers generated in odd stem in the positive cone and row divisible towers in filtration f equals 0. There's a shifted copy of B1 times x over e of 1, at least in the positive cone. The negative cone part is technically a submodule. And there are also row pairs where you can multiply by row as well. And in our paper, we describe this more explicitly, but in general, what these X groups when k is specifically larger than m looks like is you have a triangle formation portion, you have these row divisible or row towers, you also have this copy of x over e of 1, and the row pairs. So this puts us in good shape to then actually compute the KUR relative atom spectral sequence that we're interested in, because we now have all of the information that's on the E2 page. So just as an example of the types of arguments that went into this, I'll go through atoms differentials of length 2 originating in B1 torsion. So first, we want to consider the B1 torsion classes in the E2 page. And these specifically consist of V0 towers in that triangle formation, row towers, so those are going off to the left, in odd stem infiltration f equals 0, and also row divisible towers in filtration f equals 0. So any potential targets for these differentials have to be V1 torsion by V1 linearity. And V1 torsion classes in filtration F greater than 0 are contained entirely in the V0 towers. at least at the E2 page. And so the row and row divisible towers, these can't support differentials because, well, the V0 towers, they didn't have any non-zero multiplication by row. And so that leaves us to consider the V0 towers in the triangle formation, but all of those are in odd stem, and Adams differentials decrease the stem by 1, so those also cannot support Adams differentials. And so at least on the level of like the E2 page, there are no D1, there are no differentials on these V1 torsion classes. And similar types of arguments, considering the filtration and also the motivic weight of all of the elements, show that actually there are no non-trivial D2 differentials, and so as a whole, for each K, the spectral sequence that we're interested in does indeed collapse. And this means that the classes that we're interested in, these survive the spectral sequence, and so we get our desired splitting. That up to 2 completion, there is a splitting of KUR modules in terms of the sum of these shifted copies of the C2 equivariant integral Brown-Gettler spectra and KUR. So there are also a few other ways that we can present this splitting. One is in terms of Adams covers. So if we let KUR upper brackets n denote the nth Adams cover of KUR, up to 2 completion, smashing KUR with the kth integral Brown-Gettler spectrum can be decomposed into the Adams cover, some with an part that is just suspensions of the Eilenberg-MacLean spectrum. So this is very similar to the splitting with the CKs and the VKs that we saw earlier. And because of this, well, up to 2 completion, we also get a splitting of KUR smash KUR in terms of these Adams covers. Moreover, along the way in computing the KUR relative Adams spectral sequence, we also computed the KUR cooperations algebra. So the KUR cooperations algebra, KUR star KUR, this splits as a sum of the shifted by row KUR homology of these C2 equivariant integral Brown-Gettler spectra. So the pictures that go along with this are the simpler X groups, those where you just take X over E of 1, shift it to the left, and start adding on X over E of zeros. And as part of showing that there are no differentials in the KUR relative Adams spectral sequence, well, one needs to be sure that there are no differentials coming from the negative cone summands hitting things in the positive cone summands. And there's a large enough gap in motivic weight that no such differentials can occur. And so because the positive cone summand computation really is separate from the negative cone summand computation, one also gets the analogous motivic analog result with the KGL cooperations algebra, and also a splitting of KGL smash KGL in terms of Adams covers as well. And the computation also gives rise to the KUR operations algebra. So this again splits as a summation over K of shifted suspensions from the integral Brown-Gettler spectrum into KUR. And the pictures for this are the more complicated X groups where we have a long lightning flash module in the first factor and M2 in the second factor of X. So these are the ones with the triangle formation, the row pairs, the row divisible towers, and the shifted copy of X over E of 1. So some new directions that, given the splitting that are currently in progress with Guchuan Lee, Jackson Morris, who's a student at University of Washington at Elizabeth Tatum, are that we're beginning to compute the KUR-based atom spectral sequence. So we want to do this to investigate what C2 equivariant stable stems can we compute with this sort of tool. What can we say about V1 periodicity? How much does this spectral sequence highlight it? Can we use it to identify V1 the image of J in the atom spectral sequence for the sphere? And another project that we're thinking a bit about is, can we construct a similar splitting for KOC2, smash KOC2, and if we can ask similar questions about what we can deduce from the Wood cofibration, which relates KOC2 with KUR, and similarly ask questions about KOC2-based atom spectral sequences, C2 equivariant stable stems, and V1 periodicity from that perspective as well. So to give an introduction in that direction, and this also appears in a current preprint, so if we wanted to start computing the KUR-based atom spectral sequence, well, the E1 page has a form where we're taking homotopy of KUR smashed with the cofiber of the unit from the sphere spectrum into KUR. And so what the KUR splittings imply is that we get a really explicit description of the E1 page in terms of smash of KUR with suspensions of the C2 equivariant Brown-Gettler spectra. And moreover, we also know how to compute the homotopy of those smash products. Those are some of the simpler X groups that we saw, which have M2 in the first vector and L of M in the second. So some additional further directions that may be broadly of interest would be to connect some of this work with the KUR cooperations algebra with a description in terms of numerical polynomials. This is done in the non-equivariant setting. There's a very explicit description with a periodic version, but then also some of that follows through to the connected setting as well. We additionally constructed an HC version of the splitting. So it may be interesting to try out some HC-based atom spectral sequences. Berglund and Strogowski have an obstruction theoretic construction of BPs, so maybe something similar could be done with BPR as a nice example. And also the computations we do are some of the same as some of an obstruction theoretic construction of KO or BO Brown-Gettler spectra. So perhaps we'd be able to construct higher C2 equivariant Brown-Gettler spectra. But that approach also requires some analysis with the lambda algebra, so that may prove to be rather difficult. So not sure there. And then in related just fun things, I do have some postcards and stickers that are related. So these are a bunch of shifted suspensions of E of 1. And I guess there's a little bit of time for questions.
Questions first, Pete.
I don't think you explicitly said, but do you have any control over the product structures and cooperations of the operations?
We just did this additively. We didn't think about it multiplicatively.
Yes. Do you have any equivariant analog of the story about loop 2s3?
Yes. So the equivariant analog of that is with loops rho, S rho plus 1. And that's how the C2 equivariant integral Brown-Gettler spectra that we're using were constructed, is that we took a filtration on loops rho, S rho plus 1, and bootstrapped up from that in order to get the C2 equivariant integral Brown-Gettler spectra analogs.
Maybe more basic, but how did you define these motivic Adams covers of KGL?
Like the same sort of definition as classically. Yeah. So just follow the same thing. Yeah.
Do you mentioned this classification of equivariant E1 modules that you guys used. Could you expand on how you did that? I think classically they use kind of Margolis homology computation or something.
Yes. Yeah, so we did something similar. So we bootstrapped up from the C motivic to the R motivic, and there's work of Bhattacharya, EU Lee, and then also there's another paper, Isaacson, and I'm forgetting the other co-author, but there's like two papers where some Margolis homology over C and R appear, and we bootstrapped that up to C2 equivariant, specifically using adding the condition that the homology be free over M2, and then also using the fact that rho is in the center of the Hopf algebroid, and this allows one to have enough control to get similar Margolis homology results.
Maybe you mentioned this in the middle. Are these equivariant Brown-Gettler modules injective in any suitable sense? Like, are they?
So that I would love to know, but I don't know the answer currently. Yeah.
You mentioned some AU-based aspects of computations. Can you
Yes.
form some kind of
Motivic version of it, I guess like Gonzalez's weight spectral sequence, and do the computation like that, or how are you guys planning to do that? Just out of curiosity.
Yeah, so right now what we're working on with this is we're doing pretty similar analysis to the paper that's like on the E2 page of the BO-based atom spectral sequence with, Mark, I forget the co-authors that are on there.
This is like a 5 on.
Yeah. Yeah, exactly. Yeah.
Agnes and Bhattacharya, Jolie, myself, Culver.
Yeah. So far what we're trying is starting with that as the underlying story and seeing what differentials we can lift to the C2 equivariant. The nice thing about R motivic is that then you don't have these negative cone summands floating around. So an R motivic version would be very similar to what we're doing, just chop off the negative cone summands, and so there's less to bookkeep. But so I expect something would be possible. Maybe that hopefully answers part of your question.
All right, so thank our speaker again.